for this fossil foraminifera data table, we're going to be filling these out with the information. So that's what this 1 through 4 is showing. And so that's this data table here. You'll see that we're going to look at this drill core, drill hole 105, drill hole 10, drill hole 11, and drill hole 137. So here's drill hole 105, drill hole 10, and then on the next page here is 11 and 12. And note that at each of these, for example, this drill core 137, they drilled right here. And this strip is a paleomagnetic signature of the seafloor during this interval of time. But more importantly, we want to see the marine sediment. So note that they had clay particles, very fine-grained clay. Then they had this marly ooze, which is basically calcareous ooze. Eventually will form limestone. Right below the limestone is a basalt. So the limestone immediately above the basalt had these microfossils. And in fact, what I want to go show you is I want to do hole 105 here. And so note hole 105 is this hole here. And this is a paleomagnetic signature. But right at this hole 105, note that they had limestone. And the limestone right above the basalt had these 4 plankton, these 4 foraminifera fossils. Remember, foraminifera are calcareous and eventually make the rock limestone. So on the preceding page here, we have the age ranges for all the different types of plankton, foraminifera, and going back to geologic time, back to about 160 million years old. Remember, the seafloor is no older than about 160, 180 million years because eventually it gets subducted. But note that for that whole 105, we have these 4 fossils, and those 4 fossils match up with this Brotozenia, Biardia, Sacocoma, and Lenticulina. And in fact, I've sort of already drawn them out. So I've drawn them out here on my hole 105, and I've colored it so I can show you these on the graph here. So on the graph, it's these 4 fossils, right? And these lines represent the age ranges for each fossil. So for example, Sacocoma first came into the fossil record, first appeared in the fossil record at this point during the Oxfordian, and then it went extinct at this point during the Tithonian, right? So those are the epochs that we're talking about. Brotozenia starts in the early Oxfordian and goes extinct at the end of the Kimmeridgian, right? So that's what we're going to be charting out. So on our fossil foraminifera data page, we want to see the geologic epoch associated with the fossils at hole 105. But before we do that, let's just name those fossils so we have them all here in order. So for these, we're going to have a Brotozenia, Biardia, Sacocoma, and Lenticulina. So I'd like you to write those down. Write the ones that because you're going to be doing the other 3 holes, right? And so we want to figure out the key thing. We're looking at overlapping age ranges. We did this with the geologic time lab on fossils, right? It's the same thing we're going to do. So in this case, we want to figure out when all these fossils coexisted in time. So one thing about Lenticulina has a very long lifespan. We're not going to worry too much about because Lenticulina first came into existence during the Oxfordian, or maybe even before, because I didn't show where it starts here, but it went extinct up here in the Cenomanian, so it had a long history. So the ones that had shorter history are going to be better index fossils, right? Remember, an index fossil has a short duration. And so one thing that I note is the oldest this sediment can be, it can be no older than the first appearance of Sacocoma, because if it's any older, then I will not have this fossil in my sediment. So that's going to be my baseline. So I'm going to put my ruler here at the bottom and draw a straight line all the way across, all the way to the numbers here, because eventually we're going to get the ages there. And so note that line that I drew crosses all 4 ranges of all 4 specimens, all 4 fossils. Now the youngest it can be, I can't pick anything younger than Kimmeridgian because Brotozenia went extinct. So that's my limiting factor for the upper limit there. And so there's already a line drawn there, but I'm just going to extend this line out to the numbers here so I can see the numbers. So when they're asking, what is a geologic epoch? So the epoch is, so I would say it's late Oxfordian to Kimmeridgian. So that's what you want to put down. You want to put the age of the epochs there. And then they want to know the range of million years based on just the fossils, right? Based on those epochs. And you see it goes from 151 to about 157 or so. 157. So about 151 to 157 million years. So that's what you want to put down for the age ranges, 151 to 157. And then now this is where it gets interesting. Now they want you to do the Paleomagnetic age. And this is what I'm going to show you next. So note that at the very end of this lab, on the Atlantic side, or the Africa side of the Atlantic Ocean here, there's this little magnetic strip. And you're going to have to cut that out with scissors. And I've already cut mine out. And so this is what it looks like right here. I've cut it out. And now what I'm going to do, I'm going to use this to figure out the Paleomagnetic age. So I go to this hole 105 here, right? And I'm going to use it to match the signature, the magnetic signature on this area of the seafloor with my magnetic strip that's calibrated for ages. And so remember, we're getting this calibration for the Paleomagnetic ages here on the side. So magnetic reversal scales here. So we can chart these going back through time. Right? So basically it's the same little strip here, but it's in a form that I can cut out here and we can look at. So one important thing when you're using the magnetic strip, because we know the seafloor spreading states that the seafloor is younger at the ridge and older farther away. So when you're measuring or using the strip, make sure 0 is toward the ridge and it gets older as you go farther away. When you're doing hole 137, you're going to have to flip this thing around and have 0 at the ridge and make it go older in the eastward or Africa direction, right? All right, so let's see how we're going to use this for hole 105. So one thing you're going to do, you're going to, in fact, what I recommend is you notch out where hole 105 was drilled. So it was drilled right there. So when we're looking at this Paleomagnetic age, you see the match is right there. And when I bring this over, it's about 156 million years, 156. So that's what we're going to record on our map here, 156 MA. And note that that fits within the range of our fossils, right? So now your job is to do the same thing, but I want you to do hole 10, hole 11, and hole 137. So now let's look at some of these questions. So question 6 is going to ask you to draw isochrons on your map passing through each drill hole parallel to the ridge rift axis. And so we want to draw isochrons on both sides of the mid-oceanic ridge. So we're going to draw those 4 isochrons at the correct distance. And I'm going to show you how to do that. So here is our map. So you're going to have to cut, and usually I cut this Africa side of the map. I cut it along the ridge axis, then I tape them together to make the whole seafloor. And I've already drawn the isochrons through the holes. There's hole 11, hole 10, 105, and 137. And note that I've drawn them at an angle because I want them to be parallel to the ridge axis, right? So they should be parallel to that ridge axis. Now, we know that hole 105, based on the fossil and the foraminifera, we said it was 156 million years old. So that's the age, or the isochron age for hole 105. So we want to show the other 156 age out over here on this side of the mid-Atlantic ridge, on the east side of the ridge. So the way we're going to do that is we need to measure along this dotted line the distance from the ridge axis back to the mid-ocean, to the isochron. You could count individual dots and do it, or you can just take a ruler. In this case, I'll take my ruler, and I'm just going to start here with 0 at the isochron for 156, and I'm going to curve it along here until I reach the ridge axis. See, I get 11 centimeters, right? And so now I'm going to take that same action there, put this at 0 here at the ridge axis, and then I'm going to measure 11 centimeters out to here. And so you'll see that's going to work out to be somewhere in here. And it doesn't have to be perfect, but I do want you to show both sides. And again, I'm going to be parallel to this ridge axis, and I'm going to draw my isochron right here. So that's my isochron. That's 156 MA. So 156 million years ago, North America and Africa were that much closer. They were at the ridge axis. So the isochron 156 was at the ridge axis, and then since that time they spread to their current location. So you're going to do the same thing for hole 10. You're going to measure this distance and then measure it out over here. Draw your isochron 10. You're going to do the same thing for hole 11. Draw your isochron for hole 11. And then measure this distance out to hole 137. And then you're going to draw your isochron for 137 out over here somewhere. So you're going to show 4 isochrons on both sides of the mid-oceanic ridge. Then the next thing they're going to ask you, now we're going back to that rate problem. So again, the distance over time. And here, I looks like I want you to do it in kilometers per million years. So let's keep that in kilometers per million years. And then when I say we want to figure out, so we're going to figure out the rate between hole 10 and the ridge axis. And we're going to use that rate to calculate the when North America and Africa started separating, or basically when Pangea broke up. And we'll do that when we measure across this 200-meter line. So if we look at that, you'll see that there's this 200-meter depth along North America. So we want to measure from there along this dotted line that goes by Bermuda there, all the way to the ridge axis, right? We want to measure that distance. And note here, one important difference for this map here is that the scale now is 1 millimeter is 20 kilometers, right? So that's going to be our scale. So figure out how many millimeters you have here, multiply those by 20, and you'll get your distance in kilometers, right? So that distance will be divided by the rate you get for from hole 10 back to the ridge axis. So and then that'll give you an age, and your age should be in the between 180 to 200 and a little over maybe 200 million years. So we'll see what you guys get there. And then the last question here: why was there no if we look at this sediment here, there's no sand. There's no sand there. And for hole 105, note also here there's silty clay, dark clay, limestone, no sand. Why is there no sand? Well, if you think about where is sand, where do you find sand? Well, sand is primarily found over here along the shorelines. It's too heavy to reach the deep ocean. So you want to answer that question to the effect of that. But anyways, I think that answers the questions, and then I'll be available during lab as a conference Zoom to kind of tidy up any questions you may have. So see you guys tomorrow.